Hello and welcome to the Object-Oriented Programming in Python Masterclass. This course is the only course on object-oriented programming in Python that you need. Most courses that cover object-oriented topics may show the basics, such as what classes are, what instances are, what methods and attributes are, and maybe even touch on inheritance and magic methods. But usually that's it. In this course we cover everything from beginner topics to advanced topics like descriptors and metaprogramming. After completing this course, you will be definitely proficient enough to independently implement very complex Python projects with OOP. So let's take a detailed look at what this course includes. So we start with the basics because fundamentals are always the most important. We'll explore what classes are, what instances are, how data is stored in classes and instances, and how functions and methods work within classes. Then we dive deep into magic methods. These are special methods in Python that start and end with a double underscore. In connection with this, you will also learn about operator overloading and how it relates to magic methods. Next, we move to single inheritance. Here you will learn about how to inherit methods and attributes and of course why you want to do that. We will also learn how to extend built-in classes like dictionaries for inheritance with custom functionalities. After that, we will have a look at what slots are, why they are needed and how to inherit with slots. Then we explore some special classes in Python, namely Dataclasses and Enums. We're also gonna have a short look at the patentic library here. Next, we delve into multiple inheritance and mixing classes. You will learn how Python handles multiple inheritance under the hood with the method resolution order and how to dynamically compose your own classes using mixing classes. After that, we move on to properties. We'll explore how attributes differ from properties and how you can control the reading and changing of attributes through getters and setters. Now comes the perhaps most challenging topic in this course, descriptors. Here you will learn what the descriptor protocol is, what data and non-data descriptors are, and how you can make classes much more dynamic with these getters and setters. Then we'll have a look at abstract classes, known as abstract base classes, or in short ABCs. These are essentially blueprints for blueprint classes. We also cover a very advanced topic that you'll probably never need, but it's still very interesting to know, metaprogramming. Metaprogramming in computer science involves creating programs that generate other programs. With metaprogramming, you can actually modify the functionality of Python itself, which is a very cool topic. At the end, you will basically know everything about objects in Python, but you may ask, how to use that knowledge in the real world. Very intelligent people came up with how to organize objects in Python, so-called design patterns. I will also show you the most popular patterns in this course. If that sounds awesome, stay tuned, we jump straight into the basics. Okay, I am in my IDE. I use PyCharm to write the code, but of course you can use any other IDE like VS Code if you like that more. It works the same everywhere. So I created a new file called basics.py, and this is where we will write our first class. To write a class, you have to use the class keyword, and then you have to define the name of your class. You start your class name with a capital letter, and the rest is written in small letters. So I will create an archer class, and first we're just gonna write pass here. So the class is not able to do anything right now. We can use that class to create multiple instances of that class. To do that, we have to define a new variable name. And now we have to use the class name and write round brackets. So this will create an instance of that class, and we can create another instance like this. Then we call it archer2, and we can create as many instances as we want. So currently this archer doesn't have any attributes or methods, and to add an attribute we can just write archer1 and then dot, and then we can define an attribute name, for example HP, 4 hit points, and set this to 100. And then we can also print these values, of course. So let's print archer1.hp, and now use a terminal and just run python basics.py, and here we can see in the terminal it prints the value of this HP variable. If we want to print a variable that does not exist, we get an attribute error. To be honest, what we just did is not the best way to add an attribute. Python gives us the freedom to do so, but the instance here does not reflect the blueprint. It is better to define what attributes and methods our archer should have directly in the class. So to do this, there is a special underscore init method for this. So first let's remove this here and this, and also the second archer, so we only got the instantiation of the single archer. And instead of pass, we write a function or method here, and this is the init method. So the first argument is self, So this self here means that this init method is an instance method. So it does not belong to the class, but it belongs to this instance. And in here we can also write pass, and the code will just work like before, so no errors here. If we want to add attributes, we can do it like this. So we write a comma after self and then HP. And here you can see the IntelliSense function directly complains. So parameter HP is unfilled. To fix this, we're gonna remove this pass here. And now we're gonna write self dot and then the name of the attribute we define in this function. So self.hp equals HP. So this is the dynamic value we pass in when we instantiate our class. So this is the same like before, where we directly created this HP attribute on the instance, but in this case it's dynamic. Let's add a second attribute, which is mana, and do it again. Self.mana equals mana. And now again we can see parameter HP unfilled and parameter mana is unfilled. So we can set the HP to this, HP equals 100 and mana also equals 100. If we don't provide the name of the attribute, we can also use positional arguments and do it like this. So this will be HP and this will be mana. Okay, now we created an archer with dynamic attributes. Now let's add a method. A method is just a function inside a class which starts again with the self as first argument. So let's call our function shoot, and as you can see, PyCharm directly creates the self for us as first argument. And we can do whatever we want here, for example just print shoot. So now we can use that method, so archer1 dot and then shoot. Instead of just printing the attributes, we have to call this method here. So this works just like a normal function. So we can do this multiple times. And as you can see, now we got shoot, shoot, and shoot. We can also work with attributes with a function or method. So we add another attribute here and add it again here. So now this archer has got arrows. Let's say we've got 3 arrows when we start with a new archer. And now when we shoot, we want to decrease the arrows attribute by 1 each time we shoot an arrow. So we can first check if self.arrows is larger than 0. So now we can still shoot. We can print archer shot. Let's do this in an F string. And then do it like this. Self.arrows left. And if that's not the case, we want to print archer cannot shoot, no arrows left. So now let's run this 4 times. And yeah, one issue is of course that we don't decrease it. We have to decrease it here. So self.arrows equals -1. So now we decrease the arrows. And now we can see archer shot 2 left, archer shot 1 left, archer shot 0 left. And the last iteration here is archer cannot shoot, no arrows left. Okay, now let's learn how classes actually work under the hood. So if we have a look at our archer, let's just print the archer here. We can see that this is just, of course, archer1 is the name. Let's do it again. And this is just the reference in memory. But we can also print all of the attributes. We did it before like this, so we can use arrows, we can use HP, but we can also print all of the attributes, and this can be done with the __ dict attribute. So if we run that, we can see that a class stores all of the variables in a class dictionary. So we've got HP 100, mana 100, and arrows 3. We can run all of the dictionary methods here, so we can also access attributes like this. So there is no black magic behind these attributes. It's just everything stored in an instance dictionary. We can not only store attributes in an instance, but we can also directly store them in the class. So to do this, we just have to define a variable here, and we call that species. This will be a string, and we just call that human. So if we have a look at our instance dictionary again, So nothing really spectacular. We don't see this variable, but if you try to call it like this, so archer dot and then species, we don't get an attribute error. And this is how Python works under the hood to reference attributes. So if we try to access one specific attribute, Python first searches in the instance of that class, and if that's not found here, then it looks in the class itself, so it looks in the blueprint. And if there's no attribute 2, then it will raise an attribute error. So when do we want to use an instance variable and when do we want to use a class variable? So if you want all instances to share this species variable, then we have to set it directly in the class. Otherwise, we set it here in the init method. We can not only set class attributes, but we can also set class methods. To do this, we have to define another method here. We just call this CLS method. And now this also gets a self, but to prevent this, we have to write a decorator over this method. And here we use class method. This is built into Python. And instead of setting this to self, we just call it CLS. This doesn't really matter because this is just a naming convention, but this indicates that this method here, this CLS method, does not belong to the instance, so it does not belong to the archer, but it belongs to the archer class. So not to archer 1, but the blueprint. Okay, so here we can just print I am a class method. So let's try to run this archer1 dot CLS method. And if you run this, we can see that this actually works. So this works the same as for class attributes. If Python does not find a method that belongs to an instance, it searches for a method that belongs to a class. So when do we want to use a class method? Most of the time you see class methods to provide alternatives to the init method. So instead of creating an instance like this, we can create a class method and create an instance from that. So now let's create a different class method and we call that from string. So now we want to create an instance from a special string. So here we provide the class itself and then we provide a data string. And what we do with this data string is we split it and pass in the attributes from that string to the constructor. To do this, we want to split that string. So we run a string method, datastring.split. And here we want to split like this. So we want to split by minus signs and we want to save that in a new variable. So we want to extract HP, mana and arrows from that string. Here it's called arrows. And to do this, we can use the map method and pass this here. And what we also want to do is we want to map this to an integer. So this will now extract all of the values. So this is a list. We'll convert that to an integer, each of the values, and assign that to HP, mana, and arrows. And then we want to return the class which runs the constructor. So this runs the init method and do it like this. So HP and then mana and then arrows. So this will also create an instance. So now let's do this. So instead of doing this on the instance, we directly do this on the class. So archer dot and then from string. And the string has to look like this. So first we define a string and then we say 100 minus 100 minus 3. And if we run archer2 dot shoot, or let's make this 5. So we've got a different example. We can see archer shot 4 left. So this creates also an instance of that archer. Besides class methods and instance methods, there are also a third type of methods, which are static methods. To define a static method, we have to use the static method decorator, which is also built into Python, and then define a function here. So we just call it static. And if we run brackets, we can see that we don't have to pass CLS and we don't have to pass self. So this static method is independent from any variables of that instance or of that class. So here let's just print I am static, and we can do that on the instance and see I'm static, and we can directly also call that on the class itself. So this works for the class and it works for the instance. So when do we need this? So static methods can be useful if you need functionality related to a class, but it does not need access to its instance or class-specific data. So in general, if you have got many static methods in a class, think about, does that class actually, or does that method actually belong to the class, or is it better just to write a normal function? Most of the time, when you find yourself writing a static method, it's better to write just a normal function. Great, so now you've learned the very basics of object-oriented programming in Python. Now let's move on to magic methods or dunder methods. Let's first create a new file. We call that magic methods.py, and we copy the archer into this file. So remove the class attribute, but that's now fine. Okay, so first let's create an instance of this archer, and we want to print the archer1. So first we provide HP, mana and arrows. So let's run it with Python magic methods.py, and this is how our archer looks like in memory. This is the normal representation of our object. We can change that behavior by using a special dunder method. Dunder method means these to underscore in front and underscore then at the end of the method. So these are dunder methods or magic methods. The init method you already saw is a dunder method, and we will have a look now at the wrapper and str dunder methods. So we will define a function called underscore underscore str and underscore underscore, and here we can say we want to return a special type of string which looks different from that, and this will now override this representation we've got here. So we can just return a string like this, and if you run it again, then we see that we just get archer now, and we don't get this memory representation. We can provide a little bit more information here. I would recommend using an f string, and then for example with self.hp and self.mana and self.arrows. So if we do it like this, we can print our instance and see, of course we have to write HP here and self.mana and also arrows. So now we can see how many HP our archer has, how much mana and how many arrows. We've got another dunder method which looks very similar, and this is the wrapper method. So repr, and here we can also return a string, and this is normally a more technical way to represent our class. So we may do it like this. So here we do self.hp and here a comma, self.mana and another comma, and here self.arrows. So here is the round bracket around that, and now let's run it again. And as you can see, nothing happens. So we still get archer with 100 HP and 100 mana and 5 arrows. If we remove that method or comment it out, we can see the following. So now we can see this is the wrapper method, which now prints our archer. We can also see 100 HP, 100 mana and 5 arrows. So the default behavior is that if we don't implement any of these, the representation of the object will look like this. So if we provide the wrapper method, then the wrapper method is used. If we provide the string method is used. If we provide both, then the str method will overrule the wrapper method. So when to implement which? In general, the str method is for the user of your class, and this is for the developer, so for you who actually writes that class, and this is for the user who maybe uses your library. So this was about the representation of an object. We can also add objects in Python, at least some objects. So you can add 5 plus 5. Let's do this. So let's print 5 plus 5, and this will result in 10. So in Python, everything is an object. We can call 5 plus 5, but actually there's an object that calls a special dunder method, and this is the __ add method. So that's actually happening under the hood. I'm gonna show you that. So we can do it like this. So we print 5 and we have to wrap around the 5 in brackets and now call the __ add method and now add another object which is also 5. So if you print this, we can see that this also returns 10. So when we run this, actually under the hood, this is happening. So what happens if we try to add two archers? So let's create another archer, archer 2. And now let's print archer 1 plus archer 2. So if we do this, we can see we get a type error, unsupported operand for archer. So this does not work, but to make it work, we can just implement an add method here. So we can just do it like this. So we add this, and this add method has got an attribute which is other. So we have to add the instance, which is the first argument, to another class. So normally this is of the same instance, so we only can add archers. We can check if the other object is not an instance of archer. So if not is instance other and of what? Of archer, then we want to raise an error or return an error. So return a not implemented error. Otherwise we want to do the following. So we want to create a new variable called new HP, which is self.hp plus other.hp, then new mana, which is self.mana plus other.mana. So we calculate the HP and mana and also the arrows of both instances, and then self.arrows plus other.arrows, and at the end we want to return a new instance of archer, which has got new HP as HP, new mana as mana, and new arrows as arrows. So now we can do this and save it in the variable archer 3. And now we can print archer 3. So if you run this, we can now see that we've got an archer with 200 HP, 200 mana, and 10 arrows. We can also overload other operators, for example the equality operator. So let's print if archer 1 equals archer 2. If we do that, we can see that currently we get a false. We will later learn why this is actually happening, but currently I would expect that if the archer has got the same HP, same mana, and also the same number of arrows, that this would return true. So we have to implement this on ourselves. We can do this with def __ and then eq for equality, and here we can just do the same like before. So if that's not an instance, in this case we don't want to return a not implemented error, but we can just return false, because if that's not an instance we cannot compare it, and this is always not the same. So if that's an instance of archer, we can do like this: self.hp equals other.hp and self.mana equals other.mana. So we check if the archer instances got the same HP, the same mana, and also self.arrows equals self.arrows. At the end, this will either return a true value or a false, so this will return a boolean. And if you run it again, we can now see that now our comparison returns true. If we change it, let's say we make 6 arrows, then it will return true. If we remove that and want only to check for HP and mana, then this of course will return true. We can also check if one archer is larger than a second archer with this. So we could normally check is 5 larger than 3, and we can do the same for custom objects. So if you run that, we can also see that now we get an error because this is also not supported. So we have to implement this on our own, and we do this with the GT, which means greater. And In this case we do it like before, so if that's not an instance of Archer, we want to return not implemented. So maybe let's have a look at how this actually looks. So let's do it like this. So now we get the same error. So Archer1 larger than 5 does not work in this way. Okay, so if that's the case, if we've got two archers, we should now get not an error. As you can see, this returns none because we don't return anything, but we don't get an error anymore. So what we can do is we can just return, and then again the same like here. In this case we can make it easier. Just do self.hp is larger than other.hp. So we only compare the hit points of those two archer. In this case we can see false because both have got 100 HP. So if we make it the other way around, so if we want to compare like this, so is archer 1 smaller than archer 2, do you expect an error or not? I can tell you this directly works, and this is because when you implement one method, you also implement the opposite. This is very convenient by Python, so this will automatically return this in the other direction. So this will look like this. So we only have to implement this GT method. The opposite is actually called LT, and yeah, we don't have to implement it, but you have to know if you want to have a different behavior, then you have to change it. So let's say we want it like this, then this is totally unnecessary to implement. So this returns the same value as before, but let's say here we want to check for equality, then we get true, but yeah, it does not make any sense. Normally you only implement one of these and the other is automatically implemented. Okay, let's now have a look at the __ hash method. And the hash method is needed if you want your instances of a class be able to be a key in a dictionary. So let's try this. We create a new dict. So new dict equals a new dictionary, and we now set our archer as key, and we provide a simple value like test. So will this now create an error or will it work? So if you have a look at it, we can now see that we've got an unhashable type archer. So to change this behavior, we have to implement the __ hash method. And what we're gonna do is we want to return a value that does not change over time. So we could just return like a single number, like 1, and then we've got no more error. So we can see, okay, this is still a comparison, but yeah, so this can be now a key in a dictionary, but normally you want to do something like this. So you want to call the built-in method called hash, and you want to run this hash method on an attribute of the class that does not change over time. So in practice you often see something like this. So we hash self.hp. So we first create a tuple like this, and also self.arrows and self.mana. So this works fine, but what might be the issue is that if we change that value, archer.mana equals, let's say, 200, then this key is not consistent because we would now have different hash. And this can lead to potential errors in the lookup process of a dictionary. So you probably don't want to do this. You often see this in other tutorials, but I think it's a very bad practice. So a better way to do it is just import a value, a library called UUID. And now you want to create a new variable called ID, and you do that with an underscore. That shows the user of your class that the ID should not be changed. And now you just call UUID, and here we create a new UUID, and now we hash that private ID. So instead of doing like this, we do like this. Okay, let's maybe just go back one step and actually print the hash of our instance. So we print hash and then archer1. So now we can see this is our hash, and if we change this, let's say this is our first hash, and archer1.mana equals then 100, and we print it again, we can see that the hashes change over time. And this is what we don't want. So if we change that to self_id and run that again, we can now see that the hash stays consistent. And we want a consistent hash in our dictionary. Okay, let's extend the example a little bit. We now want to create a new company class where we can assign archers to. So we create a new class, which is called company. And in this class, we want to put multiple archers in, and we want to do this with operating overloading. So we use an init method, and in the init method, we want a single argument, which is the size. So we cannot put infinite numbers of archers in the company. We only can add up to 5 archers. So we first create this attribute for the instance, self.size equals size. And then we also want to be able to iterate later over the archers. So we create a container, which is called archers, and this is just an empty list. We also create an index variable, which we use later to iterate over this list, and set it initially to 0. So now we have to create a method which can add instances of archer and put it into this archers attribute list. So we create a new method, def add archer, and this takes a single argument, which is the archer itself. And if that is not an instance, is instance of an archer, so not other, but this, then we want to raise a type error, only archers allowed. If that's an archer, then we want first to check if the length of that list, so length self.archers is greater than self.size. Then we also want to raise an error. In this case, we want to raise a value error, company already full. Otherwise, we just want to run self.archers. So we just use a simple list method, append, and then we append the archer instance. So let's actually try it out. So we create a new archer. Let's say it's archer 2 with 100 HP and 5 arrows. And then we want a new company. So let's call it just company. And our company has got a size of 5. So now we can just run the method add archer, and we add the archer 2 to this company. So we don't get an error, this is fine. And yeah, let's comment that out here so we don't print anything which is not related to our company. Otherwise, we just want to run self.archers. So we just use a simple list method, append, and then we append the archer instance. So let's actually try it out. So we create a new archer. Let's say it's archer 2 with 100 HP and 5 arrows. And then we want a new company. So let's call it just company. And our company has got a size of 5. So now we can just run the method add archer, and we add the archer 2 to this company. So we don't get an error, this is fine. And yeah, let's comment that out here so we don't print anything which is not related to our company. So this works fine, but instead of running it like this with a method, we want to do this with operator overloading. So we want to calculate company plus archer 2. And if you run this, we can now see again that this is not supported. So we have to implement the __add method. So def __add. And first we want to check if that's an instance of archer. And if that's not the case, we can just raise a type error. That's also fine. Only adding archers allowed. Okay, so now what do we actually do? So we want to append this archer to the list, so to this attribute. So we're gonna run self.add archer, and we pass in the instance of our archer, so this. But we have to return something from here, and we have to return the company. But first, let's maybe analyze what happens if we don't return anything. So we save this in a new, so new company equals that. And now we print company dot archers, and we also print new company dot archers. So let's try it like this. And now we can see none type object has no attributes archers. So this does not work because we don't return a company object, but we return the value from here. And if we return nothing, then we return none, and we cannot access an archers attribute of a none type. The fix is actually quite easy. So we have to return from this method just the instance itself. So we just right here return self. If we do this, then we can see that now we've got this company, and if you run that again, let's check it here, then we can see that now the new company is the same like this company. So it's actually just a copy of that, and we can add as many archers as we want. So let's add 3 archers this time, and let's remove that. So now we can see that we've got a company with 3 archers. Okay, let's say we want to iterate over our company and print not just the list, but we want to print each of the archers. So what we want is for archer in new company dot archers, we want to print the archer. So this works of course fine because we've got a list and we can iterate over a list. But actually it would be much cooler if we can do it like this. So we just iterate over the company itself and not over the archers attribute. And now we get an error, type error, company object is not iterable. So we can actually change that behavior too with the iterator protocol, which is implemented with the __iter function or method and the __ next method. So let's first define the methods. So def __iter and def __ next. In the __ next method, we can work with the index, which we defined here, which starts with 0, and we use that to increment step by step over the length of our list. So we do if self.index, if that's larger or equal than the length of self.archers, then we know that we exhausted our iterations. Then we want to raise a special error, which is the stop iteration error. From this next method, we want to return an object, and this is the archer at the position of that list, which we access with the index. So we do it like this. So we create a new archer instance, or create a new archer, better said, and access it from the archers list. And here we index it with self.index. So we, in the first iteration, we access the element with index 0. So we access the first element of that list, and we just return that archer. But if we keep it like this, then we would always return the same archer, and this loop would work forever. So we have to increment the index by 1. So we do it like this. So this now increments the index by 1. So now we've got this __ iter left. So iter takes an iterable object and returns an iterator for it. So allowing the object to be traversed through iteration. So we need to define this so we can actually run the next method. And what do we want to convert to an iterator? This is the list here. So we're gonna just do it like this. So we run iter on self.archers. And of course we also have to return that. Okay, now let's try this again. And we can see this works. So we now implemented our own iterator. So I have to admit, actually we don't need to use this. This was just for demonstration purposes. So how to make use of the next method by increasing an index and then raise a stop iteration error. Since we use the built-in list from Python, this list already implemented this next method, so we can just get rid of it and use this under the hood. So we only need this iter method, and we can also get rid of the index. And if you run that code, it still works. So normally you don't want to create your own iterator protocol, but just make use of it like this, so you can loop over a custom class like this. Great, that was already a lot to learn. Let that sink in, make a break before we start exploring inheritance. Inheritance in Python, a key concept from object-oriented programming, enables a new class known as a child or subclass to derive properties and methods from an existing class, the parent or base class. This mechanism offers several advantages. Firstly, it allows for reusability, since a subclass can leverage code from the base class, enhancing modularity and maintainability. Secondly, inheritance facilitates extensibility. A subclass can not only inherit, but also expand upon the functionality of the base class by adding new attributes and methods or altering existing ones. Lastly, it establishes a clear hierarchy among classes, simplifying the understanding of relationship between various program components. Through inheritance, Python programmers can create more structured, efficient, and scalable code. Okay, for inheritance, let's create a new file called inheritance.py. And in this file, we won't use the archer class directly, but we will create a base player class. So we just call it base player, which has got an init method. And here we pass in HP for hit points and allow to set that in the constructor. And then we define another method called walk. And this will just print I am walking. So this is now our base player, and we want to create multiple other classes, child classes, based on that base player as base class. So how do we do this? So first we will create an archer, or let's first create a wizard, so a different class, and now we want to inherit from that base player. We just have to use round brackets now, and here we put in the name of the class we want to inherit from. And then if we just type pass and create an instance, so let's create a wizard just by creating it like this, and we pass in HP, then we can run the method walk. So let's execute that file, python inheritance.py, and we can see this works. We didn't define any walk method in the wizard class, we just inherited it from our base class. So we get the functionality and also the attributes from that base class. Let's now create our archer class. So let's just create it here, archer, and this should also inherit from the base player. And now we will create another function called shoot. And this is just the print statement, archer shoots. So let's create an archer. Archer is an instance of archer. Let's give the archer 100 HP. And now let the archer walk and let the archer shoot. So this works fine. The archer is able to walk and is able to shoot. However, the wizard is not able to shoot. We can try that out. Let's do it like this, and we could now see that we've got an attribute error. Wizard object has no attribute shoot. So this won't work, but that's how we can define different behavior in different classes. So we can inherit functionality we want in all classes. We can define that in a base class and then extend the functionality here in a different class. When we only want an archer to be able to shoot, then we can just implement that functionality in the archer class. Okay, now let's say we want our wizard not to be able to just walk, but to be able to float. But we want the method also be called walk. So how would we do that? We could just override that. So we define another method here called walk, and here we just override the behavior of our base class. So here we just could print I am floating, and if we now, let's remove that, and if we now to call that, we can see that it prints I am floating. So if we implement a method with the same name as our base class, the method in our child class will override the method of the base class. Okay, now let's say we don't want our archer to only have HP as attributes, but also have arrows. So how can we do that? So we could do it like this. So we could define another init method and then pass in the attributes here like HP and arrows. And now we could implement that again, self.hp equals HP and self.arrow arrows equals arrows. So what's the issue with that? So we write duplicated code, and instead of just inheriting, we override this method and define it new again. So we define the setting of the HP attribute here instead of using it from the base class. So that's not the way we want to do it. PyCharm also complains. We can see call to init of superclass is missed. So this is what we're going to do now. So instead of doing it like this, we will use the HP from the superclass. We could do it like this, base player, which has got the init method, and here we pass in self as first argument, and then we pass in HP, which equals HP. So this is how we could do it. And if we have a look at our archer now, so now let's comment the wizard out and comment that in. We can see that we are missing an attribute here, and we want to define the arrows. So okay, now if we instantiate that, or let's say shoot, and maybe instead of just printing shoot, we can also decrease self.arrows by 1, and now print self.arrows arrows left. Okay, so now let's try to shoot again. And if we have a look at that, we can see that this now works. So we've got our HP, which we inherit from the base player, and we've got the arrows which we define in the child class, so in the archer class. So this works, but it's not the best solution. And why is that? Because if we change the name of the base class, so if we call base player, let's say just player, then we would have to make changes in multiple parts in our code base. So for here, it's totally fine because we actually change the name of the class, but for here, it's not necessary. We can do it better. So what we can do is we can just, instead of naming that player, so for here it's necessary, and for here too, but instead of doing here, we can call a special method, and that is super. And this super will now make the whole process dynamic. So no matter how we call our base class or our parent class, this will always call the correct superclass. So instead of here just doing it with self, we can remove the self argument and just passing the attributes here. So, and if we run it again, we can now see that it still works. Instead of just inheriting from our own classes, we can also inherit from built-in Python classes. So let's have a look at an example. So I create a very simple dictionary, which I just call X, and the key in the dictionary is test, and the value is 1, 2, 3. So now let's just print X. And yeah, I think that's not really surprising. We can see that we've got a single key and a single value. So what happens if I now do this? So again, I set the key to test. And if you run it again, we can see that if we already got the key in a dictionary, then the value we set here will override the old value in the dictionary. Instead of writing it like this, we could also directly access the key in brackets, so test, and this equals 200. So there is no difference. But let's say we want a different behavior. Let's say we want a dictionary that will raise a value error if we've got a key already present in our dictionary. So we can do this by inheriting from the dictionary class. So let's define an own class and call it no update dictionary, and now we inherit from the built-in dictionary. And the built-in dictionary has got a special dunder method called setItem, so __ setItem. And here we've got a key, so this is the key, and this is the value. And now we can check if that key is already present in that dictionary instance. So how would we do that? We would check if key is in self, so if it's in that instance yet. If that's the case, we now want to raise a key error. So key already present. And otherwise, we want to call the superclass, so we want to call the setItem method of the built-in dictionary and call it like this. And here we pass in the key and the value. So that's the default behavior from the dictionary, and we only want to check here if that key is already present here in that instance. And now we can create our own dictionary. So we call it, let's say, y. This is an instance of no update dictionary. And now we want to set a key and set it to 1, 2, 3. So now let's print x. Let's maybe remove that. And okay, that's of course not x, but it's called y. So let's print y, of course. And now we can see this totally looks like a normal dictionary. But if we now try to do this and set it to 200, so instead of overriding it, we now get a key error, key already present. So in this example, you can see the power of inheritance. So instead of implementing everything on your own, you can take other people's classes and extend on that as you wish. One little fun fact now. You may ask yourself when creating a new class, you've got this init method, you've got this dictionary method. So where do all these methods and attributes coming from? In Python, everything is an object. And in Python, there exists a root object, which every other object automatically inherits from. So under the hood, actually what's happening here is that you inherit from this. You inherit from the built-in object. This is how code was written in Python 2, but in Python 3 you don't have to do this. This automatically happens under the hood. Great, that were the very basics of inheritance. We're now gonna have a look at special classes called Dataclasses and Enums. So let's now create a new file called Dataclasses and enums.py. And before we dive into data classes, we're gonna create a bow class, but do it with the normal way. So we just create a class like this, class bow, and create an init method here. So we want a name for that bow, we want a price, and we want damage. So now we can set the attributes like this, as we learned before. Self.price equals price, and self.damage equals damage. Now we can create a new bow like this. So bow A equals bow, and here we pass in the name as first argument. Let's just call it great bow, and then the price is 100 and the damage is 20. Okay, that's the way we can create a new bow, and we can access the values by accessing the instance dictionary. Let's just try that out. So data class in enums.py. Of course we have to print it. Let's run it again. And now we can see these are our values. So what's now special about this class? This class only contains attributes but no other functionality. So it's just a data container. And exactly for these kind of classes, data classes were introduced. To create a data class, we have to import that from the data class package. So from data classes, we have to import data class. Data class is a decorator we can use above a class. So we can write it like this with the @ symbol. And here we just write data class. And now if you write a class like this, so we create a new bow, but this time it's a data class. We now have a data class, and we have to type it a little bit differently. So it works like this. So instead of writing an init method, we just write it like this. So we just want this name attribute. Then we write double colons and then the type of our value. So this is a type annotation, and we want the name of the bow to be a string. The price should be an integer or a float, and we can do it like this. So price, then double point, and then float. So this is the data type for price. And then the last one, damage, and this should be an integer. So we just type int. And now we can create a new bow like this. So bow1 equals bow. And here again, we pass in the name like before. So we just type great bow. Then price is, let's say, $9.99. And the damage is 20. Okay, now we've got a new bow, but the syntax is a little bit cleaner than before. Another advantage besides the syntax is the following. Let's create another bow. Let's call it bow2. And as you can see, all of the values are exactly the same. So now we want to compare bow1 and bow2. So we write bow1 equals bow2, and we will get a true or false. So under the hood, a data class implements a lot of the dunder methods we learned about in the chapter before. So what we can also do is we can use the wrapper method. So we don't have to write it, but if we just print bow1, we can see that the data class implements a wrapper method. So we can see it like this, and not like I just showed here again, where we print this bow A. And here it looks like this. So here we can see just the object in memory, but below we've got a nice wrapper method. So this is nice, but of course not every dunder method is implemented. So if we do something like this, so is bow1 greater than bow2, we can see type error, so comparison like this is not supported between instances of bow and bow. So we would have to implement that on our own. We can also set the data class to frozen, and I'll show you the impact of it. So we can do something like this. So let's print bow1, but before we want the bow1 attribute price, and we set it to 150. So if you run that and print bow1, we can see that we changed the price. If we set the data class to frozen, so we just have to type frozen equals true, then we can see cannot assign to field. So this is another dunder method, setAttr. So this dunder method, which was implemented by the data class, now raises a special frozen instance error. We can also change the behavior by adding some other attributes here. So what we did before was compare bow1 to bow2 like this, and this raised an attribute error or a type error. Type error not supported between these instances, but we can just change that by setting order to true. So if you run it again, we can now see that we get a false. This comparison takes all of the existing attributes into consideration. So not only the numeric values, but also the string. So if we do something like this, we can now see, okay, we have to do it like this. So first value is greater than second value, because the Z comes after the G in the alphabetical order. We can also remove some behavior. So if we print bow1 again, we see that we've got this wrapper method, but we can also disable that. So if we type wrapper equals false, then we can see the standard representation of this object. So as you can see, data classes offer a lot of benefits, but they also have a little drawback, and that is the missing type checking. So let's say we want to change our price to a string and just type in expensive. So we can see that PyCharm is clever enough to display that there is an error. Expected type float got str instead. But if we actually call that, so let's also set the wrapper to true so we can see it. Yeah, the class is created and there is no issue with it. These missing type checks can of course lead to runtime errors or any other unexpected behavior. So I want to show you another way to create classes which look like native data classes but offer type checking, and this is the Pydantic library. You can install it with pip install Pydantic. So the library is itself written in Rust and adds a Python wrapper around it, so it's pretty fast. And Pydantic influences many of the most important libraries in the Python ecosystem, like FastAPI or LangChain. Now let's create a bow with Pydantic. So instead of using a decorator, we have to import a base model. So from Pydantic, import base model, and we have to inherit from that base model. So the class is bow, and that class inherits from the base model class. And then we use the same syntax like before. So name is a string, so we use type annotation, price is a float, and damage is an integer. So now let's create a new bow. So there is one difference. So if we create a new bow, we can not just write great bow and then 99.99 and then 20. So Pydantic does not allow positional arguments, so we have to use named arguments like this. So name equals great bow, price equals that, and damage equals 20. So now we can run it again, and this works fine. So if we just print it, we can also see that Pydantic offers us a special wrapper method. Looks a little bit different from the data class, but I think it's also readable. So now the difference between a data class, or the major difference, is that if we change the price to expensive, we can now see that we get a validation error. Input should be a valid number, unable to pass string to a number. So if you want type checking and a data class like syntax, then use Pydantic. I also got a full course for free on YouTube if you're interested in a Pydantic deep dive. Now let's have a look at another type of data class, so-called enums. Enums allow you to work with categorical variables. So as an example, we've got 3 different weapons, a sword, a bow, and an axe, and we don't want to use any other weapon. With a normal data class and even with Pydantic, that is not possible. We can see we've got this name attribute, and this is always a string, so we can type whatever we want. So this is why we have to introduce an enum now. To create an enum, we have to import the enum class from the enum library. So from enum, import enum. Important, you don't have to install the enum, it's part of the standard library. So let's create a new class called weapons. And this class inherits now from enum. So it looks a little bit like here, like in the Pydantic library. So we inherit from the class, and now we get the functionality. To set up an enum, we normally do it like this. So we set a character, which is an abbreviation for our value. So S would be a sword, or we could also write it like this. So it doesn't really matter, but you don't have to write it as a string. So B equals then bow, and then A equals X. Now let's create an instance of that enum. So we create a bow, and the bow is just the value here. So we type in bow, and now we want to print that bow. So let's run the code. Of course, we have to first comment that out. And now we can see this is how it looks like. So now we can see we've got this B attribute, but normally we would like to see the value. So to do this, we have to access a special attribute of that instance, and that is the value attribute. So now we can see the value is bow. So this is what we entered here. We can also use aliases. So if we do something like this, so instead of just writing S equals, we can now write sword equals, and the values are the same. So if we do it like this, and we now enter here bow.s is or equals bow.sword, this should return a true. Normally for an enum it's better to write it, by the way, like this. So use uppercase values, and this also returns true. Enums, by the way, work great in combination with Pydantic. So if you have complex data types to validate, then Pydantic and enums are a perfect match. So I'm gonna show you a more difficult use case for that. So we create a new class called Armory, and this Armory class inherits from base model. So we comment that in again. So this inherits from base model. And what we want here is just a very basic validation for the number of rooms in that armory, but we want a very complex validation for the weapons. So we just type here weapons, and the weapons are a list of that enum class. So if we now create an instance of armory, so armory equals an instance of armory, and we have to pass it by name. So room equals 3, or we can say rooms. I think that's a better naming. And now weapons equals, and then we have to provide a list here, and now X, and then sort. So let's print that class, and we can directly see input should be sort, bow, X, or sort. So this is a little bit weird because we use an alias here, but in general, if we make it like this, so use sort, then we don't get an error. And Pydantic is very cool since it allows us to convert the class here also into a JSON format. So now we can see that we've got this in a JSON format, but keep in mind that enum is not converted into a native Python object. It's just a list of enum instances. Okay, we are now at the end of the section. So to summarize, if you have got classes that only are data containers, use data classes, or if you want validation, use Pydantic. So you can also combine that with enums to create even more complex data types, and if you use Pydantic, even get validation for that. In the next section, we have a look at a different topic called multiple inheritance. Okay, now let's dive into multiple inheritance. To do this, we first have to create a file. So multiple inheritance.py. And we start by creating some very simple classes. So we create a new class called A. And this class has got a method called sayHi. And it only prints hello from A. And now we want another class called B, and this class inherits from A and will print hello from B. And then we create another class called C. It also inherits from A. Again, we create that sayHi method and will print hello from C. And now what's new is the following. We create another class called D, and this will now inherit from B and C. So first we type B, then a comma, and then C. And now we will just run parse here. So we will create a new instance of D, and now we want to run sayHi. Okay, what do we expect to happen? What will be printed? So let's run Python and then multiple inheritance.py. And as you can see, the D instance prints hello from B. So why is this happening? So this is because of the method resolution order in Python. So the first step where Python looks for this method is in the D class. It does not find sayHi there. Then it will go up in the hierarchy and it will go from left to right. So if we would change that from C to B, then we would see hello from C. Since it is found here, then it will not look again in that B class. If we would remove that or name it differently, then it would work in this way. It would print hello from A. So it would look in D, would not find it. It would look in C, would not find it. Look in B, would not find it. And then go back from B to A and there in this class it finds say hi, and this is why it works. If we would not have it anywhere, we would get an attribute error. So when should you use multiple inheritance? In short, you should not use it anyway, since it can lead to complex hierarchies and make it very, very hard to debug due to its tight coupled classes. In programming, in general, we prefer loose coupled objects. One exception of that are mix-in classes. Mix-in classes are classes that extend the functionality of a class, but they are not able to do anything on their own. They can just be used by other classes as an extension. So let's first comment that code out and create a new class. And here we stick with the archer. So an example we used before already. This archer has got an init method. And in that init method, I forgot this. So we want to provide HP. So here we set HP and self.hp equals HP. Then we want another method called walk. And here we want to return I am walking. Okay, now let's create two mixin classes. The first is a JSON mixin. So this is very common. We want a class that is able to output our class dictionary as JSON. So let's create a new method called toJSON. And we first have to import the JSON package. Import JSON. And now what we're going to do here is we call JSON.dumps. So the first argument is self, and then we want to provide the information what we want to convert into a JSON. And here it's helpful to use a lambda function to make it more general. So we want this lambda O, this is just a placeholder for object. And what we're going to do is we use the object's class dictionary and convert that into a JSON. So this is our first mixin. Now let's create another mixin which directly influences the behavior of Archer. So we call that class superWalk mixin, and this class has got a method called walk. So it has got the same method like this, but it extends the way this method works. So what we're going to do here is we return in an f string super. So we call a super class, but as you can see, this is nothing we inherit from. So we don't inherit from Archer directly. So we don't couple the classes, but we just want to use the functionality or extend the functionality. So we do it like this. So then we call super.walk and then extremely fast. So as you can see, PyCharm complains because we don't have a reference. So this will not work standalone, but it has to be used in combination with a class that actually implements that method. So let's now create a new class, class superArcher. And this class inherits from multiple other classes. So we inherit from Archer, we inherit from the JSON mixin, and we inherit from the superWalk mixin. So again, like in the example above, the order matters. So we first have to provide the mixins, since otherwise this would not work. I'll show you how this failed. So JSON mixin is not as important as the other mixin. So let's first import the Archer, and then we import the superWalk mixin. Here we just type pass. So now let's create an instance. A equals superArcher with 100 hit points, and we want to print a.walk. So what do you expect? So we use that superWalk mixin here, but the output is different. So I am walking, and this is because the method resolution order finds the walk method here in this Archer class and will not look for it in the superWalk mixin class. So we have to first use the mixin, and then after that use the Archer class. So now it works. I'm walking extremely fast. Let's also try the JSON method. So a.toJSON, and here we get none. I made an error, we of course have to return that value. So now we can see that we've got this dictionary here as a JSON object. It looks pretty much the same in the terminal, but it's not the dictionary, it's JSON. Okay, that was the multiple inheritance section. So again, a little warning. If you think about using multiple inheritance, then it's probably a bad idea. The use cases are really extremely rare. Okay, that's it for multiple inheritance. In the next section, we will dive into properties and getters and setters. Okay, now let's create a new file called getters and setters.py. So maybe first question, why do you actually need getters and setters and what are they? So getters and setters in Python are used for encapsulation and allowing controlled access and validation for an object's attributes rather than direct manipulation of the attributes. I'm going to show you a little example. Let's now create a new class called Archer, and this Archer has got the init method with HP. So self.hp equals HP, and now we create an instance of that Archer and we provide 100 HP. So if we print the instance dictionary, we can see the following. So Python getters and setters.py, and yeah, that's what we expect. We get a dictionary HP and the value is 100. So we can of course change that value by just accessing the attribute with a dot and override it with, let's say, 200. And then if you print it again, we can see that we changed that value. In Python and in programming in general, you normally want to control how users of that class access and change that value. And this is what getters and setters are for. So I'm gonna show you a little example how we can do it better. So one convention in programming and in Python in general is that we make this attribute private. So in Python, privacy of an attribute does not really exist. So if we run that, we can see that now we got two attributes, one attribute which we created actually here and this private attribute. But we can of course also change that private attribute. So this does not really change the behavior, but it's just a naming convention. So maybe let's not print a dictionary, but let's just print this HP. And now we can see that we get an attribute error, but we can always print it like this. So since normally users should not be able to access our private attributes, and this should not happen too, we can use a special decorator, which is the property decorator. So we just type in property. This is a built-in decorator from Python. And we now have to create a function, and the function name has to match the attribute name we want to access. And inside that function, we can now define the behavior. So in this case, we want just return the private HP attribute. And now, as you can see, there is no more error. So let's remove that. So we create a private property, but access it via this function. And actually, that's the cool thing about this property. We don't have to run it like this. So this would also work, but it would look a little bit weird because an attribute can be just accessed without brackets. And this is what the property decorator allows us to do. So that seems to be a little bit black magic, and normally courses don't cover this, how this works under the hood. But of course, in this course, you will learn about it. So you already learned about class attributes and instance attributes. So we can also, instead of doing it like this, we can create a class attribute and just set it to 50. So in this case, we would now get the value 50. And we can make use of that behavior. So if an attribute is not found in the instance, then Python will look in the class for it. So instead of hard coding the value, we can use a special function called property, which is built into Python. And inside here, we can provide an fget and an fset argument, also an fdelete, but this is normally not used or rarely used. So fget is a function which we did not define yet. So let's just type 3 dots, and fset is also a function. And now we have to actually create that function. So we can create that. So So let's just write get HP, and this should just return self and then the private attribute HP. So we can now use this, and the setter function looks like this. So set HP, that takes in a value because we want to change it, and self._HP equals the value which we provide in that function. So now let's do it like this and remove that. So let's say we now run this. So we create an instance of Archer, and now we want to access the HP attribute. It is not found in the instance since we only have got this private attribute, and now Python looks in the class attributes, and this class attribute is a function which then calls a getter function or a setter function. So before running the code, let's maybe add here a print statement, getter called, and for the second function let's print setter called, so we can see what actually happens. So let's now run that code, and we can see the getter was called. So again, we try to access the HP attribute. It is not found in the instance. Python looks in the class itself, finds the property function which calls then get HP, and this is why we can see getter called. So let's do the same for the setter. So archer.1 HP equals 200. This will then under the hood call the setter function. Here we can see setter was called, then the getter was called, and we print the value of the attribute. So this can be quite helpful to actually make some checks. So let's say we don't want the HP to be above 200. So if value larger than 200, we want to raise a value error. HP can be 200 at max. So let's try to set it to 201. And now we get a value error. So in this way we can control the behavior when someone wants to override an attribute. But of course, like I said before, in Python, real privacy does not exist. So a user of our class can always do this if he wants to do it. So we can see getter called, and now we got the HP value which was called by the getter, and it's 201. Even if we wanted to prevent that, it's not generally possible in Python. Okay, now you learned the magic behind getters and setters. So now we can use the syntactical sugar which allows us to write more readable code. We also explore a use case of getters and setters where it makes sense to use them. So let's now take that code, comment it out, and create a new Archer class where we use the property decorator and implement a little bit more complex task. So we again create an init method, but this time we pass HP and we also pass damage. So let's do it like this. So self_HP equals HP. So we set it as a private property, and self._damage equals damage. We also create a static attribute which is crit, so we can make critical damage, and the critical damage is multiplied by the normal damage we provide. So we create another property, also a private one, overall damage, and that is none at the beginning. Now we're gonna first create a new getter. So this time we use the decorator and also create a new function called damage, where we just return self_damage. So let's now create a new archer. Archer1 equals an instance of archer, and this archer has got 100 HP and 25 damage, or let's say 20 damage. Okay, now let's run it again. Getters and setters.py. Of course we want to print archer.damage, so we want to check if the getter works, and if you run it again, we can see that we now get 20. So now let's do the same for our overall damage, and this is a little bit more complicated. The reason because I just did not do that, so this is _damage multiplied by self.crit, and if we now print that underscore overall damage, then the following happens. Now this works, 26, but of course, if I change an attribute, let's say we change underscore damage, and let's make it 30, then we can see that the overall damage does not reflect the correct value anymore, since it should be 30 multiplied by 1.3. I said before that this is in general anyway bad practice, so setting a value for a private attribute is bad practice. So to do it better, we want to create a setter first. So we create a setter for damage, and this is done the following way. So you write an add symbol as decorator again, and then the name of the function. So here we've got this fget and fset, so we can exit it like this. So it's damage.setter, and this is now our setter function. So this is the getter, and this is the way we create a setter. Name of the function and then setter. And here we have to create another function. This has to match the name of this function. So it's def dmg, and here we provide a value for the setter, and the value is self underscore dmg equals the new value. We also want to update self.overall damage or underscore overall damage and set it to none. This is done because we want to make use of a caching mechanism, so we don't want to compute self underscore damage multiplied by self.crit every time we want to access this. So we only want to calculate that value for the getter again if self underscore damaged was changed. So let's first reset this initial value here to none, and then we want to create a getter for overall damage. So we want to access it like this. So currently that's not possible. So let's create the getter function. We use the property decorator and create a function called overall damage. Again, this has to match the name of the attribute we want to access. So it takes 0 arguments, and what we want to do here is we want to calculate the new value for that. So self underscore overall damage equals self.damage multiplied by self.crit. And we want to return this from this function. So we return self underscore overall damage. So let's now run it. And now we can see if we change that value, let's maybe do it like this, because we now created a setter and we can do it better. We can see that if we update that value, the overall damage is also updated. So this is fine, but there's one more issue. And let's say the calculation of that derived value of overall damage is computationally expensive. So let's say we assume that this takes 3 seconds to complete. So let's import time to fake that. So if you run it now, we can see that it's quite slow. And if we do it again, let's do it 3 times, then we can see it's computed again and again and again. So this makes our application quite slow. So for the first run, it totally makes sense to calculate it. For the second run and for the third run, it does not make sense because we did not change that value and we don't have to recalculate overall damage. So we can do it a little bit different. So now it makes hopefully sense why we set it initially to none. So if self underscore overall damage is none, we now want to compute that. So let's print compute. And this is normally fine, but I will set another else value here. So I will print using cache. So now let's do it like this, but maybe after that, let's set it to 40 and do it another 2 times. So now the value is changed and we computed the first time. Then we will use the derived value, use it again. Then we change the damage and we need to recalculate it. And then we again use the cache. So if you run it, we can see compute. Then we get the value, and using cache, you can see the values are instantly in the terminal. Then again, we make a compute and then we use the cache again. To make this code a little bit more well-rounded, we use another setter for overall damage. So we actually only want to prevent setting overall damage from the outside because it's a derived value. So we can again use a setter like this. So we use overall damage dot setter and then def overall damage, and here we provide a value, but actually it's not used. So here we just raise a value error and then changing overall damage not allowed. So again, let's maybe just remove that and try to set it like this. And if we run it, we can see changing overall damage not allowed. But as you know, you can always in Python do it like this. So this works, but in general, that's a very nice setup. Great, you not only learned about the property decorator, you learned about the inner workings behind it, and even learned about caching in combination with getters and setters. So good job. The next part is probably the hardest part of this course. You will learn about the descriptor protocol, a topic you will rarely find in other OP courses. Okay, you now learned about getters and setters and even about caching and lazy attributes, but what would happen if you would have to write code like that for, let's say, 50 attributes? That would be quite a lot of code. In Python, there exists a way to make that easier to implement, and that is to use special classes which implement a special descriptor protocol. So let's now create a new file called deskriptors.py, and inside this file we want to create our first descriptor. So again, a descriptor class is a class that implements a special descriptor protocol. So this protocol is like a contract, and that contract includes the implemented method. So for a descriptor, we need to implement two methods, underscore underscore get and underscore underscore set. So there's a little bit more variance, to be honest. So let's first implement that set, and PyCharm suggests that we have to provide this get argument and this owner argument. What this means, I will explain a little bit later. So we first just write pass. So this is already a descriptor, and this is called a non-data descriptor. To make a full descriptor, we also have to implement the underscore underscore set method. This takes instance and value as parameter. Again, we also just write pass. And now we can use the descriptor to set attributes in another class. So again, let's create an archer, and that archer should have HP. So we write that as class attribute, and here we pass in that descriptor. So currently we are not able to pass anything, so we have to create an init method where we can pass a single value in the constructor, since we want to provide one value for HP. And here we provide just the value, and self.value equals value. This value will also be checked in the set method, so this is very important for that. And we first want to provide 100 for HP, and for mana we want the same descriptor, but just pass in 50. The set method can again be used for validating the value we pass here. So we can just do something like this. So if value is smaller than 0 or value is larger than 100, then we want to raise a value error. Value has to be between 0 and 100. And if we don't raise an error, we can just set this attribute. And again, we can do it like this, but a better way is to set this to a private attribute, and that equals value. Okay, now we want to create an instance of that archer. So archer equals an instance of archer. And yeah, currently it doesn't work with an init because we did not create a constructor for that. But what we're gonna do now is we want to set HP to 200. So let's try that. Of course, run the correct file, python deskriptors.py, and now we can see that we get a value error. Value has to be between 0 and 100, and here is one error. So now it's correct. So as you can see, this has got the same functionality, as this. So, but it's of course a little bit more flexible because we don't have to implement the same logic for mana. So if we set mana to 100, and let's say we do it here correct in the first time, then we of course have also a value above 100, then again we will raise an error. So we don't have to do that for every single attribute. So now let's improve on that, because we don't want to set attributes again like here, but we want to set them normally inside the constructor. So we just have to create a constructor like this, init method HP and mana. So the attribute here has to match the name of this attribute. So self.hp equals HP and self.mana equals mana. So now we have to provide some argument here. Let's say this is 100 and this is 30. And here we set it to 101. And again, we will get an error. But what's very nice is that even if we do that, we also will get an error. So also this descriptor protocol is able to check values inside the constructor. So we don't have to implement any kind of logic here. This is done by the descriptor. So that works nice, but there is a little issue with that implementation, and that is the following. So I'm gonna show you that by an example. So let's create another archer. So we create archer 1 and archer 2. And this has got 100 HP and this archer 2 has got 17. So let's print archer 1 dot HP. So print it like this. And what do you expect here? So we can see that the output of that attribute is none, and that is because we use a descriptor to access this attribute, and we did not implement a getter method for that. So we first have to implement the get method, and here we just return self underscore value. So if we do that and run that code again, and we can now see that the result is 70. So again, I guess this might be a little bit surprising, because archer 1 has got 100, but archer 2 has got 70. So why is this value not 100 but 70? The reason for that behavior is that the archer class share a single instance of a descriptor for HP and a single instance of a descriptor for mana. So these instances of archer share a single instance of descriptor. This is why we overwrite the value when we create another instance of an archer. So this is not what we want. To fix that issue, we have to use the instance parameter of the setter and the getter, and we could do it like this. So self underscore data equals now a dictionary, and now we want to use the dictionary to write a new value for each instance. So we could do it like this. So self and then underscore data, and we create a new key, and that key is the instance. So we create a new dictionary, and each instance gets a new entry in the dictionary, and that is the value we provide here. So for the getter we do the same. So instead of returning this private attribute, we access the data dictionary and run the get method, since this is the dictionary and we want to get the correct value for that instance. So if we do that again and run it again, we can now see that it's 100. So let's try it again for archer 1 and archer 2. And that works, 170. But we introduced an issue. What happens if we delete now this archer 2? Now we run it again and we can see this works. But under the hood, we introduced a bug, and this can be a quite expensive bug in a real-world application. So we introduced a so-called memory leak. So when we delete archer 2, the value in that dictionary still remains. So we've got still 2 entries in that data dictionary. So we don't delete anything. And this makes this dictionary grow and grow, despite this archer 2 class is not used anymore. So that's quite dangerous, and we definitely want to prevent that. A simple solution for that problem is, instead of using a normal dictionary, is to use a so-called weak key dictionary that can be imported from weakref. So from weakref import weak key dictionary, and then instead of creating a normal dictionary, we just pass in an instance of that weak key dictionary. So the difference here is if we delete that instance, then the entry in that weak key dictionary is also deleted. So this is much better and works, but it's not the best solution. In general, it would be much better if we would not handle this in the class itself, so in the descriptor class, but handle that in the archer class, which makes use of the descriptor. So we have access to that class with the instance parameter. So instead of writing it like this, so we can get rid of that weak key dictionary. So let's also remove that import. Now we got an error here. And to fix that, we want to directly access not self, not the instance of the descriptor, but we want to access the instance. And the instance has got this instance dictionary where we can set a new attribute and we call it value. And we set it to the value that we pass here. Again, for the getter method, we have to do the same. So instead of returning self underscore data, we return instance and then underscore dict, and here we access this value attribute. So how does this influence the archer class? So let's remove that, create a single archer, and then we print the instance dictionary of that archer class. So we can see we instantiate it with 100 HP and 30 mana. And if you run that, we can see that now our instance dictionary only consists of that key and the value we provide as second argument here. So the issue is of course that our attribute is called HP, and here we can see it's called value, and yeah, that's not good. And we somehow want to make this dynamic. So we could possibly provide another argument called name and then pass it here like self.name equals name, and then create a second argument for this. So let's say this would be HP and so on. That would work, but it would make our code less flexible. So to make that code dynamic, a descriptor or the descriptor protocol offers another special method which allows us to set this dynamically. And this is called the set name method. Here we've got an owner, and very important, that name. So here we can set the name of that attribute, and self.name equals name. And now we, instead of accessing it like this with value, we can access it like this with self.name, and do the same for the setter method. And now if we run that code again, we can now see that it works. We've got HP 100 and mana equals 30. So no properties get lost and it's flexible. We also can get rid of this now because we don't need it, and it's actually quite confusing why we set an attribute here, since we anyway don't use it in a setter or the getter. So we just remove that since we don't use it anyway, and we need no init method. So if you run that code again, we can see that it works and we only have to provide the descriptor class, but we don't have to pass any attributes. Okay, last but not least, we want to tackle the method resolution order in combination with the descriptor protocol. So let's say we create another descriptor class and we call that class lives. So our archer has got 3 lives and implements just the get method. So we've got a non-data descriptor and we want to return 3 from that. So lives equals lives. And now we want to access this dictionary. And if we do that, we can see that we don't see that lives attribute, but we can access it. And again, if that attribute is not found in the dictionary, in the instance dictionary, then Python will look in a class for it. So just a little difference here in comparison to that normal descriptor. We have to create an instance because we return 3. So this descriptor does not make use of the instance, but we directly return 3, so we have to create an instance of that descriptor itself. So if we now run that code, we can see that we now see 3. So what happens now if we add this here as another attribute in the init method of the archer class. So let's do it like this. And now we want to set this to 6. So by providing this argument here in the constructor, we overrule the class attribute. But what happens if we make this non-data descriptor a full descriptor? So if we provide a set method, we just provide pass because we don't want to actually do anything with it. But if we run it again, we can now see that it's 3. And this can be quite dangerous. So the argument in the constructor overrules that value in the class itself if we use a non-data descriptor. But if we implement a full descriptor protocol, then the full descriptor protocol will overrule the value or the parameter in the init method. So again, that can be quite confusing and can be quite dangerous, but it's very important to know. So that was the descriptor protocol, a very powerful tool for Python developers. But as you have seen, this is prone to different errors. So with great power comes great responsibility. In the next section, we will have a look at an easier topic again, so-called slots. Okay, now let's first create a new file called slots.py. And before we work with slots, what are slots actually needed for? In Python, slots is used to declare a fixed number of attributes for a class, which can significantly reduce memory usage for instances of the class, which makes sense when you use a large number of these objects. And it also speeds up attribute access and prevents dynamic creation of new attributes. So in general, it promotes a more rigid class structure. Now let's create an archer class again. And inside this archer class, we create an init method again. And inside that init method, we pass in 2 attributes. And this is HP, hit points, and mana. Self.hp equals HP and self.mana equals mana. Then we create an instance, archer1 equals an instance of archer. We pass in 100 HP and 50 mana. Then we can print the instance dictionary. So we run Python and then slots.py. And here we can see HP 100 and mana is 50. If we want to use slots, we have to define slots in the class. So we do it like this, underscore underscore slots. And then in a tuple, we want to say what attributes we want to have as slots. So we want to have HP and mana as slots. We can access an attribute like before. So we write archer.hp and this returns the value of our attribute. If we try to access the dictionary, we can see that now this archer class has no class dictionary or no instance dictionary. And that's a big difference. So the attributes of our class are not stored in an instance dictionary, but are stored in slots. And slots are immutable, and therefore they don't use as much memory as a dictionary. This also implies that we cannot add attributes. So normally when we use a class dictionary, we could do something like this. So self.arrows equals 10. But for slots, that's not possible. So I said one of the advantages of slots is that we can save memory. So let's actually prove that. So let's create another class, archer2. But instead of using slots, here we will use an instance dictionary. So let's create one archer and a second archer by instantiating archer2. And there's a nice package called Pimpler or Pimpler. We can install that with pip install Pimpler. And now we can import from Pimpler a function called a size of. And we can just print a size of archer1. Here we get an error. So we can do it like this. So that's actually the function we need. And now we do the same for archer2. So let's run it. And here we can see that this class only uses 112 kilobytes, and this class with the instance dictionary nearly 5 times as much as the class with the slot. So that's a big advantage of using slots. But using slots also comes with some difficulties. One is inheritance. So if we want to create another class, so let's first delete that, which inherits from Archer. Let's call that class Super Archer, and we inherit from the normal Archer. So we want an init method, and here we want HP, mana, and arrows. So for the first two attributes, we want to call the constructor of the superclass, so this constructor. So here we pass in HP and mana, and for arrows we want it like this. Not allows, it's of course arrows equals arrows. So now we want to create a new class or a new instance. Let's call it S Archer for Super Archer. We create an instance of that, and here we pass in 100 HP, 50 mana, and 20 arrows. So if we print the instance dictionary, what do you expect? Do we have one or don't we have one? So as you can see, we got an instance dictionary, but it does not contain HP and mana. It only contains arrows. So if we add attributes in the child class, we also have to provide slots for that. So we don't have to provide, again, HP and mana, we only have to provide the slot for the new attribute. So in this case, it's arrows. And now if you run it again, we can see that now Super Archer has got no instance dictionary. Okay, so to conclude this section, don't use slots as default, but if you've got an application with high memory usage and where you create a lot of instances of a class which might cause that, then slots are a great way to reduce that memory usage. Great, so in the next section we will have a look at abstract base classes, or in short ABCs. Okay, now let's have a look at abstract base classes. Abstract base classes are used to enforce that certain methods are implemented in all subclasses, so this provides a common interface and ensures consistency across different implementations. Abstract base classes are primarily used by framework or library developers to establish a consistent interface and contract for users extending their code with custom implementations. So let's create a new script called abcs.py. And to create an abstract base class, we have to import from ABC the ABC class and also the abstract method decorator. And now we want to create a new class, and we call that class abstract archer. And this now inherits from ABC, and inside that class body we now have to define the abstract methods that all subclasses should implement. So to do this, I will create a new function or method called walk, and here we just type pass. So then we write that abstract method decorator above it, and now this is a method called walk that every subclass must implement. We cannot enforce the implementation of a certain attribute, but if a user should implement a property decorator, then we can enforce that. So let's say we've got this HP property, and we want, in this case, just pass. And here above that, we set the abstract method, and above that, we set this as property. So the user of that abstract archer must implement that abstract property. So important to learn, when you use an abstract base class the first time, you cannot instantiate that class. This is just a blueprint for another class. So if we try to do that, so we try to instantiate that and then run the walk method, so Python and then abcs.py, then we can see can't instantiate abstract class. So this does not work. So to work with an abstract class, we have to create another class called archer, and this class now has to inherit from the abstract archer class. What happens if we just run pass? So let's try that out. Let's create an instance of that. So again, let's try to implement walk here. And again, the same error, can't instantiate abstract class archer with abstract methods walk and HP. So that's a contract between the creator of that abstract class and us. So we must implement these two methods. So we actually have to do that. So we call this method walk, and here we just do a pass, and we also do it like this. And to actually make sense of that, we have to create an init method, and we provide a single private attribute HP and create a property, or use a property decorator above that and return self underscore HP. So we've got a getter method for that. So now we provide HP here 100, and now everything works. We can even implement some basic functionality inside the abstract class. So let's say we want to walk, and I just want to print I walk. And now, yeah, we cannot instantiate this class, but we can actually use the walk method of the super class like this. So here we do super, and then we call the walk method of the super class. So if we run that code, we can see that we now print in the terminal I walk. Okay, that's everything about abstract classes. They are a good way to enforce certain behavior in subclasses. In the next section, we will dive into the most advanced topic in this course, which you probably never need, but still everyone wants to learn it, and that's metaprogramming. Okay, now let's tackle metaprogramming. Metaprogramming in Python involves writing code that can manipulate Python's own syntax, structures, and behavior at runtime, allowing for dynamic modification and generation of code. So you actually change the way Python works. So let's first create a new script called metaprogramming.py, and in there we create our archer class, and this time it does not have to do anything. So now let's create an instance of that, and we first want to check the type of that archer. So let's now run Python and then metaprogramming.py. Here we can see that this archer instance is of type class archer. So let's check other types. Let's check that 5, that is of type int. So this built-in type function can be used to identify the type of each object in Python. So at the very beginning of that course, I said everything in Python is an object. So is this class definition also an object? Let's try it. So let's now try to print the type of that class definition. And now it gets interesting. This type is of class type. So let's even make it more confusing and print the type of type. So what do you expect? That is also type. So the most important part was actually this. So we use this class to create a blueprint of an instance, and we can actually use that type method to create a blueprint of a class. So in Python, this type built-in method behaves polymorphic, as it can serve both as a function to return an object's type and as meta class to create new types dynamically. And now I'm going to show you how to do that. So we create another archer class. So first let's change this to have one class attribute, and now we want to replicate that with this type function. So we create another blueprint called archer2, and now we use type to actually create a new class, and the first argument here is the name. We just call that archer2. This is the same as here above. Then we have to define bases. Currently we can ignore that. This is just an empty tuple, and then we have to define the attributes. And to do it like this, we do it in a dictionary here like this. So HP is 100. And now we can use this archer class to create an instance of that, like here. So we create this class archer2 equals an instance of archer2. And if you run that code, we can see that this perfectly works. So we can actually prove that this is the same like this if we print it. So let's print the type of archer2. And if you do that, we can see this looks exactly the same like this, only the name differs. So this works, but normally you want another syntax to implement metaprogramming. And I'm gonna delete that. And above that, we create now a new class called Metaclass. And this Metaclass now inherits from type. Besides that, we don't do anything. So again, quick reminder, the type of Archer is type. So we can change that by providing brackets here. And then for this, we provide a new meta class. So the default meta class for this is type. But we now created our custom meta class, which inherits from type, and we can add custom functionality here. So we can set the meta class to our meta class. And if we run that again, we can now see that the meta class for this class definition changed to our custom meta class. There are multiple dunder methods in meta classes, and I show you the most important ones. The first one is __call, and here we only want to print call. So we want to check that this call method was actually called, and now we return super. So we call the type class, and from the type class we call its method, and here we pass in also the args and keyword args, which we can provide here. The next one is a class method, so def, and this is called prepare. So PyCharm does this correctly. It's a class method. Actually, it's a multi-class method and has got its argument name and basis. So currently we want to ignore that, but it's there for creating class attributes. So first we print that this was called, and now from here we want to return a dictionary, HP, let's set it to 100, and mana, and we set that also to 100. The next method is new, and yeah, this is actually not correct. This is for a normal class, but since we are in a meta class, we want to do it differently. So here the first argument is the meta class, the second is name, the third is basis, and the fourth is namespace. So again, we print that this was called, and we also want to print the namespace. So actually that we can explore what is behind that argument. And then again, like for call, we call the superclass, and again call the new method, provide name, basis, and namespace. So in this case, we only intercept this and just do print statements. The same for the call method, but it helps us to understand what's actually happening under the hood. So let's now run the code to actually see what happens here when we now create an instance of Archer. So the first method that is called is prepare. So this is the first one, and this sets a new dictionary. And the second one is new. And if you have a look at the namespace, which was printed here, then we can see in our namespace we've got HP 100, mana 100, and there this module, main, a qual name, and this is the name of the class itself. So this prepare method returns this dictionary, and as it seems, this gets passed to the namespace since it's present in the namespace. So we can actually try to access this attribute inside that class. So that's a new class attribute, and that is coming from here. We can see this is coming from the meta class. So even if we try to create an instance of an Archer, so like this, and now we try to print archer.mana, we can see that PyCharm does not find this attribute, but if we print it, we can see we don't get an error. So let's maybe first delete that and delete that. So there are less print statements, and as we can see, this is 100. So this is actually this. So PyCharm complains that this is an unresolved attribute, but actually it's present, so it's injected by this prepare method. And when we use that meta class, every archer has got this mana attribute. Okay, that's cool, but what's an actual use case of this? You don't want to inject invisible variables into instances, do you? So one use case would be to implement a singleton pattern with metaprogramming. But what's actually a singleton? A singleton in Python is a design pattern that ensures that a class only has got one instance and provides a global point of access to that instance. So currently we don't have that. If we create another archer and compare the IDs of that, so we print the ID of archer 1 and we print the ID of archer 2, then we can see that these ID differ. So this is not the same instance, these are two distinct instances. So now let's create another meta class above here, and we call that meta class singleton. This inherits from type, and inside here we create a private variable which is a dictionary. And now we will override the call method. So this will be called every time we create a new instance. So we just print that call in singleton. So this is of course not self, but it's CLS, since we are in a meta class. And now we want to check if that class is already written in the dictionary. So if not CLS in CLS and then in this dictionary, then we want to add it. So we set this as key, so CLS underscore instance, and then we set this CLS as key, and the value is an instance. So we call the superclass, so we call this method and we call the call method, and here we pass in args and quarks. So every argument and keyword argument gets passed from here to here. So if we have an instance, then we want to return that instance. So we can just return CLS instances, and then we access this class which was stored in that dictionary. So let's do it again. And now we want to use that singleton meta class as meta class for our archer. So if we do that again, we create first a new archer and then we create a second archer. So let's run the code again. And now we can see that the IDs are the same. So this is now the same instance as this. We can even check it like that by creating an init method. And here we pass in HP again, self.hp equals HP. We delete this class attribute, and here we provide 100, and for the second one we provide 200. And now if we print archer2 and then the HP, what do you expect? Do you expect 100 or 200? Since we have a singleton, we can see that we've got 100. First time we don't have anything in the dictionary, and the second time we already got this class in the dictionary, so now we return it. And this is why the second time this only also prints 100, because the instance already exists. Okay, we are now done with the metaprogramming section. Use the stuff we just learned very rarely, if ever, but knowing about it definitely makes you a better Python programmer. In the next section we will dive into a very practical topic called design patterns. Okay, now let's jump into design patterns. What are design patterns and why do we need them? Design patterns are typical solutions to common problems in software design, providing standardized and efficient approaches to solve recurring architectural or coding issues. We need them because they offer proven techniques for building maintainable, scalable, and reusable code, thereby improving the quality and efficiency of your software. Design patterns are categorized into creational, structural, and behavioral types, each addressing different aspects of object creation, composition, and interaction. We start with a creational pattern, the factory pattern. The factory pattern provides a way to create objects using a separate method, allowing flexibility in object creation without specifying the exact class of the object that will be created. Okay, let's create a new file and call that patterns.py. And first we create an archer class again. We create an init method with just HP, and self.hp is HP. Now we want to create a method called walk, and this walk method only returns I am walking. Then we also want to create an attack method, and this should return I shoot an arrow. Okay, now we've got our archer, but we also want to have a knight, and this knight class shares the same interface as the archer class. So in theory we could also create an abstract class and force to implement the archer to implement walk and attack, and also the knight to implement walk and attack. But for this example, this is fine this way. And let's change the interface a little bit, because a knight does not have arrows. I swing my sword, so that's the knight. Now we can create an instance like this. So we could create archers by instantiating the archer with HP. This is what we did before, but now we want a class which does the instantiation process for us. So let's delete that and create another class called character factory. This character factory has got a method called create character, and we provide two arguments, the type of the character and the HP the character has, because the knight and the archer uses HP in the constructor. So if type equals archer, then we want this method to create an instance of that archer, and here we pass in the HP. If the type equals knight, then we want to return a knight, and again we also pass in HP to the constructor. And else we want to raise a value error with unknown character type. And now we can create that factory. So we instantiate that, and now we create an archer, not by instantiating the archer, but by calling the method create character. Here is a little typo, so it's create character, and we pass in archer, and we also pass in the HP. We can now create a knight the same way, just by passing knight as argument. So let's now execute walk with the knight and the archer, and of course call the correct file. We have to print that. So as you can see, I am walking and I am marching. These are the methods of knight and of archer. Great, so that's a common factory you will often see in Python, but I think there's a better way. In Python, functions are first-class citizens, and since we don't have any state in that class, it does not make sense to first create an instance and then call an instance method. So we can just remove that and make it like this. So we don't need a class for this factory. A function is perfectly fine. So if we remove self, and now it works like before, and this code is much cleaner. The next pattern is a behavioral design pattern, the strategy pattern. That enables the selection of an algorithm's behavior at runtime by defining a family of algorithms, encapsulating each one and making them interchangeable. So we create a new class called attack strategy, and this class serves as blueprint for concrete strategies. So here we just define an execute method and just type pass. And now we want to implement different strategies. So let's create a new strategy, a concrete strategy, which is a bow attack. And this inherits from attack strategy. We now want to override this execute method so we get a real behavior. And here we just return shooting a bow. And then we create another strategy. And we call that class crossbow attack. This also inherits from attack strategy and has got the same method, but this returns shoot with a crossbow. Okay, now we want to create an archer again, which is able to shoot a crossbow and a normal bow. So let's create a new archer class again. And this archer class has got a init method where we pass in HP, self.hp equals HP. And now we have to create another attribute, which is the strategy. So we also pass this here. And this equals the parameter. Okay, now we've got a constructor with two arguments. So this strategy will be an instance of a concrete strategy. So if we write another method called attack, we have to reference that strategy. So self.strategy, and then we call the execute method of that concrete strategy. So now we can create a concrete archer, and we pass in 100 HP and a strategy. So we just write it like this. So we pass in the class and call it. So we've got an instance of that bow attack as strategy and save it in the strategy attribute. And then we can run the attack method. So archer, well, let's print that, archer.attack. And if you run that, I will comment that part out. So we only have got the strategy pattern here. And here we get none, and yeah, this is because I forgot the return value. So if we execute that again, now you can see that the answer is shooting a bow. And now we can change that behavior on runtime. So we can, for that archer, set a new strategy, which is a crossbow attack. And now, if we use the same method attack again, we can see that we've got a different behavior. So as you can see, this makes our class quite flexible. We don't have to use any if statements in the attack method to define the correct strategy. We just change it in runtime and then call a single method. But it's very important that all classes here, so the bow attack and the crossbow attack, share the same interface. So both have to implement the execute method. Okay, the next pattern is my personal favorite, the observer pattern. The observer pattern is a behavioral design pattern where an object known as the subject maintains a list of dependents, so-called observers, and notifies them automatically of any state changes, usually by calling one of their methods. So let's now first create an observer class. And like before in the strategy pattern, this is just for defining the interface. So we want to create a single method, which is update, and this receives one single argument, which is the subject. So this is the object which notifies the observer. And currently we only use pass here. Okay, now we've got the king, which is the concrete observer. So this inherits from observer, and the king has got an init method with its name and self.name equals name. And this king also has to implement this update method. So we do it like this. So we pass the subject, and now we only make a print statement. Here we use an f string, So self.name, so this is the concrete king's name, received update from, and here we can define the subject, and the subject has got a class, and this has got another attribute called name, and we want to update if the knight is injured. So we notify the king if the HP was updated. So new HP is subject.hp. So we've got the observer, the king, and the subject, the knight. Now we need a concrete king, a concrete knight of course, and this knight also got an init method, and inside the init method we define the HP. So a change in that attribute will notify all of the observers, which can be different kings. So self.hp equals HP, and we need another attribute which is observers, and this is a list of the observers of that specific knight. So we define a new method which is able to attach a new observer to that observer attribute. So here we pass in a single observer, and we append that observer to the observers list. So let's do it like this. Now we need another method called notify, and this notify method is responsible for updating each of the observer we got in our list. So we loop over the observers. So for observer in self.observers, and here we call the update method of each of the observers we store in this list. And then we need another method which is responsible for triggering that notify method, and this is setHP. So if we change the HP to a different value, so we do it just like this, then we call self.notify. Okay, so now let's use that pattern. So we first create a knight and pass 100 HP, and then we define two observers. So we define King Arthur and another king, which is King Richard. Okay, and now we want to use the attach method to create a new observer, and now we pass in King Arthur as observer, and in the second call we pass in King Richard as an observer. And now what happens when we run the setHP method, let's say we set it to 50, then all of the observers, so both kings, will be notified about that. So Python patterns.py. Okay, so I've got a little error. Update requires one required position argument, which is the subject. So this does not have got the correct subject. So what is the subject? The subject is the instance of the knight, so we can just pass self as subject. And if you run that again, we now can see that, okay, let's maybe also comment the strategy pattern aus and run it again. And now we can see King Arthur received update from knight, new HP is 50, and King Richard received an update from knight, new HP is 50. As you can see, this pattern allows you to create a powerful event-driven system. There are much more patterns, but the ones you just learned are the most important and popular ones. Okay, now we are at the end of this course. If you like this course and appreciate my effort, please like the video, leave a comment and subscribe to my channel. Thank you very much for your support. Bye bye.